Well, in Physics 106, we've been studying electricity and electric circuits. So in this screencast, we're going to look at some key terms related to Ohm's law and also a couple of physics education technology simulations that'll help you out in this unit. So if you turn to your workbook on page 164, you'll see a couple of terms that we want to define. The first one is electric current. So if you need to pause to write some things down, that's what I recommend. Current is defined as the flow of electric charge in a circuit, and it's a way that energy can be transported. We're going to use the capital symbol I to represent electric current, and the unit is amperes, or what we call amps with a capital A. Electrical resistance is the property of a particular material that will resist the flow of electric current. So one way to think about this is if you have a wire or some kind of device, there are a lot of atoms that make up that wire, as represented by the dots in this picture. So if something has a high electrical resistance, that means that as the electrons are trying to flow through there in the electric current, they're bumping into a lot of atoms. It's very hard for them to flow through. That would be a high resistance. In the second picture, you can see that there aren't as many particles there, so it has a lower electrical resistance. It's easier for those charges to flow. And we're going to symbolize resistance with a capital R, and the unit is a Greek letter omega, which stands for ohms. Voltage is something called potential difference, and we're not going to go into too much detail about how batteries work or how potential works, but what's happening here is when you connect something up to a voltage source like a battery, it creates what's called a potential difference, which produces an electric field, and then the electrons or charges inside the wires start to move in a particular direction around that circuit. So the symbol for voltage is going to be a V, and the unit is volts. So we'll primarily be focusing on DC or direct current circuits which use batteries, but you could also think about alternating currents or the voltage source in your home. The electrical outlets are about 120 volts. Alright, so the next term is power. And we've already talked about power when we were in the motion unit, but we're going to talk about it here in terms of the rate at which electrical energy is getting transferred in a circuit. It'll be a capital P, and the unit that we've seen already is watts, or capital W. And we also have a relationship for power. It's going to be equal to the current I times the voltage V. Alright, so now we get to Ohm's law. And there's a text statement of Ohm's law, and we'll also have an equation that helps to describe Ohm's law. So the current in a circuit is going to be directly proportional to the voltage, which you see here, and inversely proportional to the resistance. So if you think about this, if you have more batteries, if you have more voltage in your circuit, that's going to make your current higher. And if you have more electrical resistance, that's going to make your current lower, so that's an inverse relationship there. Sometimes you'll see it written as V is equal to I times R. So there's a simulation which helps to demonstrate this idea. And so we'll click on that and go to the PhET website. This is one of the simulations that works in HTML. So when you get to the site, you'll see that you can click on it and it'll work in HTML5. So this helps to illustrate the relationship between current, voltage, and resistance. You can see here we have a certain number of batteries, and you can adjust and make it more batteries, and you can see the V goes up. If you make it smaller number of batteries, the V goes down, but at the same time the current in the circuit is also changing. The electrical resistance in this case isn't changing, but if you increase the voltage, you see that the current increases. Another thing that you can see is that the electrical resistance is inversely related to the current. So if you increase the amount of resistance, the current gets smaller. So you can also see as we increase the resistance, there are more and more particles going into this wire here to indicate that there's more electrical resistance. And then the arrows around that are also representing the current. So if we really decrease the resistance, you can see that the current represented here and by the letter I is getting bigger and bigger. So when you have less electrical resistance, it makes the current higher, but the voltage source from the batteries isn't changing. So that's one way that you can see that relationship between voltage, current, and resistance from Ohm's law. So if you increase the resistance, we saw that current decreases, and if you decrease the resistance, current increases when the battery voltage is kept the same. So what's the main difference between what we call a series circuit and a parallel circuit? Well, in a series circuit, by definition, there's only one path for the electricity to follow. So here we're talking about like two light bulbs being in series with each other, and this is a battery. There's only one path, and those two light bulbs are on the same path. On this one here, we have three light bulbs, and it doesn't matter if you change the location of the batteries or some locations of the bulbs. If they're all along a single path, we would call that a series circuit, or that the bulbs are in series with each other. In a parallel circuit, the electricity can take multiple paths. So anytime you see like this little, what we call a junction, or a place where the wires cross, that would be an indication that you have a parallel circuit. So in this one, we have the battery can picture electricity coming from in this direction, and it has a choice here. It can either take this path or it can take this path. It's going to split, and some of it's going to follow on this one and go through this light bulb. Some of the current is going to follow on this path and go through this light bulb. If they're equal light bulbs, equal amounts of current will go in each path, but if not, the current will follow the path of lower resistance. Here you can see we have three light bulbs in parallel with each other. And this is another way to draw a parallel circuit as well, because you can see that there are still multiple paths for the electricity to follow back to the battery. And here, even though it looks a little bit different, this is still a different way to draw a parallel circuit. So we also have additional ways that we can describe these circuits. So when you think about a series circuit, the current going through each of those resistors or light bulbs is going to be the same when it's on a single path, but the voltage will add up to a battery voltage. So the way to figure out the total amount of resistance when you have a series configuration of light bulbs is to just add them up. And I'll show you an example of this. So if you have two light bulbs, let's say that the first one has a resistance of 1 ohm and the second one has a resistance of 2 ohms. If you wanted to figure out what the total resistance is for those two combined, you would just add them up. So you'd have resistor 1 plus resistor 2. We have 1 ohm plus 2 ohms would give us a total resistance in that circuit of 3 ohms. If you had three light bulbs all in series with each other, you can see I've just arbitrarily assigned some values here. We've got 3 ohms, 2 ohms, and 4 ohms. If you wanted to calculate the total resistance of this circuit, you would just add them up. So 3 plus 2 gives you 5, and then if you add 4 more, you get a total resistance of 9 ohms. So it's higher than the individual elements in that circuit. In a parallel circuit, there are multiple paths for the electricity to follow, and so that current is going to be different through each branch or segment of that circuit. But each branch or bulb has access to the full voltage from the battery. It doesn't have to share it with the other light bulbs. The way that we calculate the total resistance in a parallel circuit is a little strange. We add the inverses. So I'll show you an example of this one. If you had a 3 ohm bulb and a 2 ohm bulb and you wanted to calculate the total resistance, you would write out 1 over R total is equal to 1 over R1 plus 1 over R2, and then you would plug in those values of 3 ohms and 2 ohms. And now you see that we're dealing with fractions, so what you're going to have to do is find a common denominator between 3 and 2. And so the best choice would be 6 ohms as your common denominator, and then 3 goes into 6 twice, and 2 goes into 6 3 times. So we can rewrite that as the sum of two fractions of 2 over 6 ohms plus 3 over 6 ohms, and then when you have a common denominator, you can just add the numerator. So we get 5 over 6 ohms. But that's not the answer to the question of what is the total resistance in this circuit, because that was giving us 1 over R total. So if we want to get R total, you can either cross multiply, and then you would have 5 times R total here is equal to 6 ohms, and then you would want to get the R total by itself, Or you can just think about taking the inverse of this will give you our total, and the inverse of this would be 6 ohms divided by 5, which would give you 1.2 ohms. So that means that the total resistance of this combination here in parallel is actually smaller. It's only 1.2. It's smaller than the individual resistances. So when you have things in parallel, you get a smaller overall or total resistance in that circuit. So if you skip ahead in your workbook just a couple of pages, I think we're going to do those examples during class, but there's another section on what if you have bulbs that have different wattage ratings or different power ratings. And we have a couple of rules, and these are stated on the equation sheet too. But we can help evaluate some of these circuits by thinking about a higher watt bulb is going to have a thicker filament and therefore a lower resistance. So you can picture that thicker filament is actually easier for the electrons to flow through that thicker filament, so it gives it a lower resistance, makes it burn a little bit brighter when things are in parallel. A lower watt bulb has a thinner filament, but the resistance is higher. It's harder for electrons to flow through that thinner filament. So if you're given a question like this, here we have two bulbs in parallel. One's a 40 watt bulb, one's a 100 watt bulb, and we're saying that it's connected to a 120 volt voltage source. Which one would have the thickest filament? Well, it's going to be the one that has a higher wattage rating, so the 100 watt bulb in this case. Which one is going to have more resistance? Well, it's going to be the one that has a lower watt rating. So in this circuit, the greatest resistance is going to be the 40 watt bulb. And is the current through the 40 watt bulb less than, greater than, or the same as the current through the 100 watt bulb? Remember I mentioned that when the current splits, more current is going to follow the path of lower resistance. And in this case, the lower resistance bulb is the 100 watt bulb, so more current is going to be going through the 100 watt bulb, which means less is going through the 40 watt bulb. And which one's going to be brighter in this case? The 100 watt bulb, because more current is going through there. And most of our things that are connected in our houses are in parallel, so that's what we're used to seeing. A higher watt bulb usually glows brighter. All right. But if things are in series, it gets to be a little bit different. So we can still use the same rules here. Which one has the thinnest filament? It's going to be the 40 watt bulb. The lowest resistance is going to be the 100 watt bulb. But here when they're in series, remember things in series have the same current going through them. So the current going through both of these is going to be the same. So what happens when you connect two bulbs of different wattages together is that the lower watt bulb is actually going to glow brighter than the higher watt bulb in series. And that's because that current that's the same between both of them is getting squeezed through a thinner filament, and that's going to make it glow brighter. Alright, and then there's another website here where you can look at a circuit construction kit and actually use this to investigate bulbs of different wattages or different resistances. And unfortunately this one only works in Java, so you're going to have to be on a device like a laptop that will allow you to run Java. I just don't have a lot of time left, but I'll just show you what that looks like. On here you can actually grab some different wires and you can grab some different batteries and build your own circuit. And you'll actually see that it's consistent with the way that we talked about connections for light bulbs in class. So you'll see that there's a connection point at the base and at the side of that light bulb. So you just connect up and make your own circuits here. And then once you get it all connected, what you can do is you can push play, and then actually didn't even have to push play, and then you can see that the charges are moving through the wires and through that light bulb. So that's one thing that's kind of interesting, that you can actually see the movement of the charges and as they go through the filament of that light bulb. Alright, and if you wanted to change some of the values of the bulbs like I did in that picture, you could just right click on them and you click change resistance, and here's I've made a 1 ohm bulb and a 10 ohm bulb. And so what you'll see here is that if I push play, actually the one with the higher resistance, which is our lower watt bulb, is glowing brighter because it's getting squeezed through that smaller filament inside the higher resistance bulb, and it'll glow brighter in series.